Good evening, ladies and gentlemen, and everybody who has chosen to join us this evening. We are very excited to be hosting our first OWASP Ottawa chapter meetup of 2025. It's 2025 already. How did that happen? I don't know. I hope you guys had a great holiday. I hope that you guys were able to relax. I know there's a lot of students here, so you're probably in the middle of your transition between semesters and maybe have a little bit of a break. So I really hope that everybody is refreshed and ready to take 2025 by storm. If you remember this time last year, we were talking a lot about large language models and generative AI and the explosion that came onto the scene at the time. We've had a couple of talks through 2024, kind of touched on that. Here we are a year later, and I'm really excited about the talk that we have tonight. And I'm going to talk all about who we will be talking. I'm saying the word talk a lot. We will be having a fantastic presentation from two speakers I'm excited to tell you about. But first, let's talk a little bit about OWASP Ottawa and the chapter here. You're at the meetup, you found us one way or another on the internet. Maybe you were referred here by a friend. Who is here for the first time? Yes, it's 5 or 6 people. If you're joining us on the internet for the first time, awesome, thank you. We hope that you come back or click through some of the other videos that we've got available here. This is a really open and welcoming space. We welcome you here, and we are happy that you've had the opportunity to join us. If there's anything about this event that you like or that you really don't like, we'd really love to have that feedback. If you're an organizer for OWASP Ottawa, can you raise your hand? Okay. Those of us with our hands raised, talk to any of us here in person this evening. If you don't want to do that, you can find us on Slack. Our OWASP Ottawa Slack has been going back, rolling through here. If you haven't grabbed the QR code, again, find one of us, we'll get you connected. By email, OWASP Ottawa or Ottawa OWASP? OWASP-Ottawa at owasp.org will get to us as well. We've got some great events that are not meetups that we do as well. Last year we did a really awesome Capture the Flag event. We've been talking about how to make that happen again. I think we're aiming at trying to do an open source intelligence workshop, maybe in the first quarter of this year. If there are other things that you are interested in, again, please tell us. This community is here for you. We couldn't do any of this without the volunteers. You just saw some of the organizers raise your hand. But that's not all of us. There's a huge group of volunteers who help to make this organization run throughout the year. A huge thank you to everybody who helps to make that happen. If you'd like to become one of us, again, I've talked to you about all the different ways you can get in touch. Please do. With that, tonight we're going to be talking about the security or lack thereof of large language models, and we're going to hear from two very knowledgeable folks on the subject. First, standing next to me here today, Dr. Guy Vincent Jourdan. I did it. Je ne parle pas français, but I try. I don't speak French, but I try. I try to get my kids speaking French. Guy Vincent works here at the University of Ottawa. He runs the IBM University of Ottawa cyber range upstairs, which is an incredible facility. If you haven't had a chance to check it out, talk to Guy Vincent. And ultimately focused on some incredible education and advancement in the cybersecurity space. Also with us today, but not here, joining us from the internet, is Bill. And so Bill and Guy Vincent have worked together on this talk. I'm not going to spoil it. I'm going to let you go from here. Guy Vincent Jourdan and Bill.
Thank you. Thanks for that. All right. So we switch that. I hope you can hear me. Can we maybe lower the light a little bit? Thank you very much. Right. Welcome. So yes, I'm Guy Vincent Jourdan. I'm a prof here, prof of computer science. I've been working in cybersecurity for a while. Well, that's don't fall asleep. I am now the co-director of the Cyber Range upstairs. So again, yeah, if you're interested in any kind of things, I can also talk about this. But what I want to discuss today, present, is a couple of research papers that are the topic of a thesis of that guy right there. Hello. So he might actually come and say something. I'm not sure. Hassan, are you going to say something? No, I'm not putting you on the spot, right? Okay, good. So the first part is thesis, and the second part of the presentation is going to be presented by Bill. Bill is my PhD student. That's some part of his research. So that's just a part of his PhD thesis. And in these two research topics that are not connected in any way, shape, or form, except that they are both about vulnerabilities or problems that we have in the deep learning space, more or less. But they are otherwise very different problems. So I'll go ahead and present the first one. I think I have to go here and push this button. And what I want to talk about here is a generalized attack on face verification systems. And this is a work that was done with Ehsan as part of his master's thesis. And this is a work that I have done with my colleague, Paula Banco, who is a researcher here, and she works in AI applied to cybersecurity in general. And you have here the references to the paper and the data that we use and the code and everything. And you also have the master right there. So what is this thing all about? Well, we want to talk about face verification system. Face verification system, what is it in general? Well, that's a system which is going to tell you whether two persons on two different images are the same person or not. So it's very simple. Here's an example. You have two faces there, and the model is going to tell you whether it believes that on these two pictures, those two individuals are the same person, the same identity. Systems like that are fairly common, and I think maybe most people here have used a system like that many times since they arrived here. Because every time you look at your phone, if you have that enabled, which I do, by the way, despite this research, this will recognize me and open up. And that's what it does. It looks at me, it decides that I am the person who owns that phone and unlocks. So that's a core system, and it's a very successful system. The way it works is, well, in order to decide whether two images contain an image of the same person, it has to first, well, detect that there is a person, so there is a face detection step. So this is the face in the image. Then it has to extract the features that it uses to evaluate who a person is. And that is dependent on the system that you use, which features it uses. But it will extract some features, and then somehow will compare the feature of image A with the feature of image B, and they are going to be somewhere in some high dimension space. And they are not going to be the same. It's not the way it works. So they are going to be close or not close from one another. So there is necessarily going to be a decision to be made, usually based on a threshold that tells you whether those two embeddings are at the same location or are close enough for those two images to be the same person, or if they are far apart, they are not the same person. They're going to tell you it's two different persons. Okay, that's how it works in general, these kind of things. Now, what's interesting is, so that's what we do. If you look at a picture, yourself, you're going to decide that, well, this is Mom, this is John, this is that. Now, in terms of computer doing that, here we are interested in neural networks. We are able to do that with neural networks with high accuracy for more than 10 years. So in 2014, we have had a system that was published that was able to recognize whether two individuals were the same in the picture, in two different pictures, about at the same rate as a human. And of course, this always gets better. So for 10 years, it's a solved problem, over 10 years now. Okay? So computers are extremely good at telling you at answering that question. So to repeat again how this would work on a current modern system, if you bring a picture to the system, you will run a first phase to extract the face of the person. Then you are going to extract the feature of that face. So take this picture, send it in this case to a neural network. This will embed your face into some space, the embedding space, which is the output of that neural network, which is typically a high dimensionality space. So that's a typical thing. You have 512 dimensions, and it's going to be normalized on a sphere. So you're going to be a point on the sphere that is of 512 dimensions. And so the first face will map somewhere on that space, on that sphere, and the second will map somewhere else on that sphere. And the decision is typically going to be if those 2 points are close enough under the threshold, then these are the same person. And if it's not, then they are not the same person. So that's how you are going what you are going to try to achieve with a neural network, trying to decide this kind of thing. And as we have said, this works incredibly well. So 10 years ago, this was better, as good as a human. Right now, it's better than a human. And it's a solved problem, basically. And this is why you can unlock your phone with that technology. So every time I look at my phone, it opens up. I am dead sure that none of you can open my phone by looking at it. I'm dead sure. I haven't tried, but I'll bet anything that this is not going to break on me. This is really a working technology at this point. All right, but here we are interested in things that break. There is a difference. It's not completely obvious to everyone, but there is a difference between the working system and a secure system. So what we have shown, what all these things are showing is that this can work and can be reliably used to open up. That does not mean at all that they are secure, just mean that under normal circumstances, they do work reliably, okay? So that's the question we're asking here. Are those systems not only working, but also secure? And if they are secure, how secure are they? If they are not secure, how bad is it? Because this is embedded everywhere, this kind of thing. So we are in security. We want to see if things work or not. We're going to pull Alice and Bob and see what they can do here. So we need Alice and Bob to test our system. So here's Alice and Bob. We have Alice, we have Bob, and we will use a face recognition system to see if it can tell that Alice and Bob are different persons. We'll hope it's going to tell that. And then we'll see what will take of us to break that system. Are we able to break it? And how difficult is it? So remember what I said. If you build a system like that, first thing is face detection. You need to extract the face from the image, and then this is going to be your input. So we'll run an algorithm on that, extract the face here, and then we'll have the input, the actual input to the algorithm, which is going to be those two individuals on the square. So they're going to be stretched a little bit, but this is what you see. Alice and Bob. Now, we use here one of these systems that have been trained that are independent from us. We didn't train the system specifically. This is it's just a working system that is, running this 99% accuracy, and we'll tell, okay, is this face the same person as this face? We put that in the system, and good news, those are different persons. Why? Because it's 50% above threshold. Yeah, the threshold here, and the distance is 1.43 in this particular instance of the system. Okay, very good. Now, what we want to do is attack the system. So we want to see if Alice can fool the system into thinking that she is Bob. Okay? So as human, if you're on that side, and you are trying to impersonate Bob as a human, what you would do is what? Well, you would probably work a little bit on the mustache, get rid of the singular, try to make that person more like that person, okay? Because that's how we analyze this image. So with a model, that's not how it works. So the modification that you have to do in order to fool the model to think that Alice is Bob is what you have just seen here. So now, with this new version of the image, Alice is seen as Bob by the system because the distance between Alice and Bob, as modified now, is 0.4, which is way below the threshold. So there has been I guess you're going to agree that the modification is, for one thing, not obvious to see, and does not match at all the kind of modification you would expect to fool the system. Why is the system now thinking that this image here is the same identity as this image here? And that's again because of the feature that it uses, but it doesn't match what you expect as a human. It is working on a different level. So here we have done that, right? We have taken the image of Alice, we have modified it so that this working system is fooled and will tell you, so Alice now will open Bob's phone, in other words. And you would probably not think that she's disguised in any way if you were to walk and see her like that. This is just Alice. Okay? All right, so let's back to the original picture now, Alice and Bob. And now let's go the other way around. Let's get Bob to impersonate Alice. Let's see if now you can see the difference. So this is Bob before, this is Bob after, and now Bob is Alice according to the system, whereas 0.5 on the threshold. So we can take anyone and make anyone look like anyone according to this working system, otherwise working system. In a way, that's kind of subtle. That's, and certainly not what you would do as a human in order to disguise yourself as someone else. Okay, that's interesting. What else can we do? Well, sometimes the point is you don't want the system to think that you are that particular person. All you want is the system believe that it's not you. So you want to dodge yourself, call that dodging. So what would it take for Alice to disguise herself in such a way that the system is going to say it's not Alice? No. Is that person the same as that person? No. So here we start with the original image. Distance is 0 because of the same image. And again, modification of Alice. And now the system is fooled into thinking that Alice is a different person. Okay? So again, I'm not sure you can, do you see the difference actually from where you sit? So there is a difference. It's not like, but it's sort of subtle. There are some changes in the faces of Alice and of Alice here. But so she's about as far as herself, so 1.5, is about the same distance as Bob used to be from her original image. And same thing with Bob. Take Bob versus Bob unaltered, and then you change it, and now the system thinks those are two different persons. So Bob is dodging itself here, the system. So if you use the system now to recognize that Bob is walking by, this will fool that system at this point.
It almost looks like just a resolution change. One is a higher resolution.
It kind of looks like that, yes. But those changes are absolutely not random. We produce them. So I'll explain a little bit how we do that in a second. We produce them, but yeah, it gives this idea that it's sort of a blurry, slightly blurry image of Bob itself. But okay, so one more thing up my sleeve here is that the image that we have used to dodge and to match are the same. So actually, you can do something like that, where the same image, so this is Alice modified, this is Bob modified, and you have the entire thing that Alice is dodging herself while matching Bob. And so we basically, it looks like we can do pretty much what we want with this thing, really. We can push it the way we want and make it believe anything we want. Now, you might be thinking, well, those are, no, this is because of this particular picture. We handpicked those two individual because that works well with them. Not quite. So I've done this presentation a few times. Usually what I do is, if I know ahead of time who is going to be in the room, and I can have a little bit of his time to pre-process the picture, I just send images of people in the room, and it does the same thing. So these are things that I've done in the past. So this is the dean of the Faculty of Engineering, and this is the Vice Dean Research of the Faculty of Engineering. And they were here for an event. And you can see that with those two persons, that works just the same way. I did the same presentation in Quebec. So those are two profs from Quebec, works just fine. This is Paula. So, and this is another colleague, works just fine. So it doesn't matter which pair of images we are starting from, which two individuals we are starting from. I can guarantee you 100%, any two of you, any two you choose, we will start from, they are different, and we will transform one into the other into one, make them, and this is going to be the level of changes that we'll do every single time. Okay, so that's not great because those are, again, the system we use everywhere. But you might say, okay, this is all cool, but this is well known. This is what we call adversarial example in machine learning. And again, that was also published 10 years ago. So now we have a name for it, so it's cool. It's called adversarial example. And this is a very famous image that was published by a good fellow at the time, where so you have this system, this is a panda, the system knows it's a panda, and then you merge this image with some noise here, and now the system is pretty sure it's a gibbon at this point, even though you still think it's a panda. So it's fairly similar to what we have done here. We had Alice, we sort of modified a little bit Alice, you're still pretty sure it's Alice, but the system thinks it's Bob. So it's a known problem. One of the things that the experiment that we did have taught, I don't know if it taught you anything, but it taught me something, is my own interpretation of that used to be that, well, okay, so I'm not great at thinking in 512 dimension. My sweet spot is 2 or 3. But so if I try to see that in 2 or 3 dimension, I'm going to say, okay, so what is happening here is that this picture goes into a part of the plan that is panda zone. And panda zone happens to be next to gibbon zone for whatever reason. And this image here, it's not a great confidence, so it might be a little bit on the border of that zone, and somehow, for whatever reason, if you put that, it kicks in to the next level up, and now it goes into gibbon. That was my intuition beyond this kind of thing. So what the work is showing, that what I just displayed, is that this intuition is totally wrong, right? That you can take anyone from any zone and move that thing anywhere on any zone with this transformation. There's absolutely no notion of this is an edge case. It's actually anything. And in fact, when I said that you can take any two person and make them map to one another, the reality is the only limitation you have is the face detection system. So if you remove this precondition that it needs to find a face, you can take a banana and make it resemble anyone. Or you can a black image, a solid color, and so it will work in any situation whatsoever. So that's not great either. It's very, very weak. Can it be worse? Well, this is answering a slightly different question. It's asking what this image is. Okay, so it's sort of a classification question. This is a panda, and now this is a gibbon. In the first verification system, the question that we ask is a little bit different. We are not asking, what is this? The system says it's a gibbon. We are asking, is it a gibbon? And the system says yes. That's what we do in this first verification. So in other words, when I look up at my phone, the system will never tell me, oh, I think this is, I don't know, I think this is Adam. The system will not say that. It just says, this is the same person as the one I have in memory, okay? So it seemed like a side thing, but there is a big difference. When you get something like that and you ask what it is, the thing can be wrong once. Like that, it's wrong, it's not a gibbon. If you ask, is it a gibbon? Then you have an opportunity to get the system wrong many times over. So if instead of saying, is it, what is it, it's a gibbon, if you ask it, is it a gibbon, it says yes, you still have an opportunity that the system, if you ask, is it a giraffe, it's also going to say yes. And that we can do with first verification system because we ask, is it that guy? So basically, when we ask, is Alice Bob? The system says yes. Is it possible that this same Alice, if you say now, is it Charlie? It's also going to say yes. So it's actually worse than what we thought it was 10 years ago. And the good news is, yes, of course, it is a lot worse than that. So it was first published in 2021. And what we got here are master faces. So faces that, if you are a little bit into keys and locks and all that, a master key is a key that is going to open different locks with different cuts, okay? So here the idea is to produce a face that is going to be confused as a lot of person or many person at once without changing the face. So in that particular paper that was published in 2021, what they do is they use a GAN to generate a person-looking image that is going to be confused with a lot of person in the data set. So we have a standard database that we use for doing this kind of this kind of evaluation so that all the systems that are being published in research can be compared with one another. They work out the same data set. And so the data set that we use has almost 6,000 identities in it. Okay, so 6,000 people in the database. And so that's what we are working against. So with that particular system here, they created that weird-looking guy, and just that guy here is confused with about 24% of the identities in that set. So almost 1 in 4 person of the 6,000 individual match that guy, according to this system. So as I like to say, this guy is the password one of biometric authentication. If you use that as your password, if you send that person in the system, you have 1 in 4 chance to get in. This other weird-looking guy, 17%. And if you collect a few like that, so for example, so in this paper, unknowingly, they were working out of a set of 9 images. I'm not sure why. But so if you get this set of 9 images, which is identical to being able to try to log in 9 times on the system, you are going to break 43% of the identities in this data set. So if you have 9 try, you are almost as 1 chance over 2 of getting in with this thing. Again, on the system that works, that is deployed everywhere. So that's excellent. I mean, from the security viewpoint. But can we do better? Yes, of course we can. So this is where we come in. This is what we have done. We have taken this problem and made it worse in 2 ways. The first thing is, right now we are just trying to match. So that's the first attack where we're talking, the impersonation attack. But as I said in the original thing, you can also dodge. And so we are trying to combine that. So in our attack, you identify the identities that you want to match, and you identify the identities that you are trying to dodge. And we'll do both at the same time. So we create identities that are going to match as many of the match set as possible while dodging all the identities in the dodge set at the same time. Just one. So that's one thing. The other thing is, one of the big weaknesses of this particular work is that those people look very weird because they are not real people. And in particular, they don't look like you. So you cannot take one of these things and pretend it's you on your badge because you don't look like that. So someone is going to spot that. So can we get rid of that thing and instead of using a randomly generated person, use an image that is imposed on us, so my picture, your picture, and use that as the basis for the attack. So in our solution, you give us the attack identity, so the person that you want to match as many people from the match set and dodge as many people from the dodge set as possible. How do we do that? The idea is that in the previous research, they were starting from the image itself, and we're trying to move here to search for a problem in the embedding space. And we realized that it was quite inefficient to do that. Instead, it's better to work directly in the embed set, try to find where you would be to maximize the damage, and then work your way back in and create the image that would embed right there. Okay, so that's what we did. We will first, in the phase 1, find where we are aiming for in the embedding space. And we will have as many dots as we have images, attacking images. So in the paper that I was referring to, they had 9 images. We'd have 9 dots there. And then work your way back into the image space to create the image that embeds into that spot. So using that, so I'm just going to skip over that. You get something like that. So here, so to show that this is, an image that imposed on us, we picked Einstein. And so this is an image of Einstein that we found on the internet. And assuming that you want Einstein to be the attacker, this is a set of 9 Einsteins that are mapping 60% almost of those identities here. So now with our attack, not only do you control the identity of the attacker, it's not some random person, it is you if you want to be the attacker, but we have well passed the 50% mark at 9 attempts. So we are at, you have 60% chance of breaking in this particular data set with 9 attempts in this particular case. And again, it's not that Einstein that does that. This is another Einstein and does that as well. Here's Alice again. And she does 57% here, and she's dodging Bob at the same time. This is my colleague from Quebec, and she does 60%. Well, on the data set. And this other guy here, a colleague, and this is the Vice Dean Research. She does 62%. Wow. Of the data set. So if you give me that many attempts, I have 62% chance of being recognized as you if you're one of these almost 6,000 identities here. And the same thing here, so etc. I'm just showing a few examples to show you that this is really not dependent on the starting image. It can be your face, can be anyone's face, and this is going to work just the same. What is what, sorry?
Is it too early to ask about the delta? Like, why isn't it consistently 80.5%?
Oh. Why is it not the same? Well, because, yeah, there is still some work to be done. So there is some loss that is happening every time we do that, right? When we identify the dots here, we cannot create an image that is going to map right there on this particular dot. So there is going to be some level of randomness, if you will, in this thing. And in addition to that, in this set here, it's not saying, but we are also dodging a different image every time. So that will also change that. So we are roughly in the 58 to 62%. But yeah, it's going to change. In fact, if you rerun that, it's also going to be changed, right? This is one run. It's not say the best run, but it's just a run. They are all pretty much there. All right. And this guy and all these guys and all these guys, et cetera, et cetera. So basically, what we show is that we can take a system like that and we can make it do whatever we want. And we are stuck with 9 or 10 images here every time just because we need to compare with previous work. But if you just give us as many attempts as we want, this is how it works. So we start at 1 or 2 attempts. We are already cracking 20% of the data set. We are at 9, 10, and we are in the 50, 60% of the data set, as we have seen on this example. It keeps growing. So if you allow me not 10, but 20 attempts, now I am at 80%. So basically, it would be completely unacceptable in any authentication system that if you give me 20 attempts, I have 80% chance of breaking in. It would not be a starter. But this is what we deploy everywhere. And that's what we use. So this is the actual state of the face recognition system that you have on your phone right now. Now, these are attacks that are done in the lab. I would not be able to make you open my phone with this type of attack. We are thinking about going further, but he graduated, so we have to find someone else to continue if someone is interested. But we can see that this kind of attack can be made a lot more practical if we localize, for example, the changes. So instead of being anywhere on the picture, if we were to add glasses, for example, and look at the change only on the glasses, which we could do, then it makes it, I think, quite practical, because then you have the glasses on you, and it just, glasses like that. And there you go. All right, so that's the first system that we wanted to talk about, face verification system, and show you. I think this research is very interesting because it shows a real problem that nobody seems to care about. It also really put a big emphasis on the difference between a working system and a secure system. And people have a hard time understanding that this is not the same thing. It can be really working well and still being quite insecure. And in this case, it's hopelessly insecure, but it's working very, very well. Does that mean you should remove it from your phone? Well, your choice. But it is as secure as that on your phone right now. Okay, so from then, there is something else that we want to discuss, which is working on this Gen AI thing that is the latest and greatest. So these things that are generating images, in this case, out of noise, and how we can poison them. So here, I think Bill is going to talk. Can he?
I'm here. I audible and all that. Nothing. I hear an echo. Okay.
As we wait for Bill, let me tell you a little bit about Bill.
Okay. Oh yeah.
Perfect.
Bill is a PhD student here at the University of Ottawa. He did his major, interestingly enough, in security and risk analysis at Penn State University. So he went the cybersecurity track at Penn State, and then received a master's in electronic and computer engineering from a university whose name I will not pronounce in Korea. If anybody can help me pronounce that, I would appreciate it. Bill, maybe you'll be able to help me. Are you here now?
Can you hear me?
I can see you, but I cannot yet hear you. We're working on it.
Okay.
So he came back from Korea and is currently working on research that intersects between synthetic data generation, which we're talking a little bit today, in diffusion models, federated learning, and AR, or augmented reality. So as soon as we have Bill successfully on the line, I was telling you at the beginning, Given said at the beginning of this, that this is the first multi-site meetup that we have done with folks on Zoom here, but I haven't done a. Oh, we got music.
Close.
Drum roll, please. Hey, it's Bill. Ladies and gentlemen, Bill Aiken.
Hello. I'm guessing I'm not visible, right? There's nothing like doing any hand motions is not going to help anybody see anything, right?
At the moment, that is
Yeah.
true.
Okay, so I'm just going to be a voice in the sky for this.
We can
We,
bring
we
you in
might wind
after.
up cutting you in on the internet. I'm not sure. So just in case, you know,
It's a little janky if we want.
it's a bit janky.
Okay, so let's
Okay.
do that first, and then we can see you.
Wait, what's the plan?
You talk.
Okay.
You change the side.
Okay. Yeah. So, hey, everybody. Happy to be here. Thanks for having me. In this, yeah, I'm going to be talking about my work, Devil Diffusion, which is all about trying to put hidden backdoor behavior into these very popular diffusion models. Gen AI's, everyone's talking about it. Diffusion models have been around for quite a number of years now. If you use those platforms like Dolly, or if you ask GPT to generate an image, or any of those ones that have that built into it now, very likely on the back end, you'll be interacting with a diffusion model, and I'm interested in breaking those. So to get started, I guess go and start the next slide. I can give a bit more context about diffusion models in general. So when we call, I mean, mute that for sure. That probably didn't sound great. Yeah, so diffusion models are actually a two-stage process. When we say diffusion, what typically people think about is the backward diffusion process, the going from nothing, from pure noise into an image. But this is actually made up of two different steps. So the forward diffusion process takes your train set of images. So whatever distribution of data you want to try to emulate or generate new images from, you'll take a collection of those, and across, well, so the most basic types will be about 1,000 steps. Across 1,000 steps, you'll take noise and progressively add it more onto the image, and eventually you'll reach random noise. Behind the scenes, there is a bit of special math that you use, a scheduler, to make sure that the noise is added in a certain fashion so that it doesn't explode in one part of the image over the other. It keeps track of how much has currently been added, so it adds a little bit less over time so that it's like a smooth transition to pure noise. But then you get to that point. And then your neural net, your deep neural network behind the scenes, usually a U-net, called a U-net because it's shaped like one. It's a U that comes down in progressively smaller things. If you're familiar with variational autoencoders, it's similar to that. Anyway, it learns how to predict what noise was added at each step, and it learns to remove that noise from your training set. So tens of thousands, hundreds of thousands of images if you're small scale. And then you give it a new set of random Gaussian noise, and it's never seen it before, and it will generate a new image, something that's not seen before, representative of the training set, but is not actually a member of the training set. So that's a lot of things, a lot of words to say what's going on here, how diffusion models work from a very high level. You go ahead to the next slide. What we want to do with this is to hide in their inherent weaknesses. So diffusion models, putting aside some of the ethical questions that people have and concerns that people have about the source of this data, whether it's been stolen or just scraped without permission, or however you want to look at it, there are weaknesses in these systems. So specifically, there are biases, and because these models are not great at language in any real fashion, they're not great with negative prompts. They also, in telling it not to do something. So if you don't want a diffusion model to generate something in your image, your best bet is not to tell it not to do it, because then it will start to do it. And you also don't have a whole lot of control, right? As a result of that. And when you tell it, you give it new noise, you don't really have a great expectation of what's coming out of it. That's compounded whenever, we get to the point that these models are pretty good. So you can go ahead and tab across, I think, 2 times. they've gotten to the point that they're, really, really, really good when we throw the entire internet of images and associated prompts with them into these models. They do start to become really good at creating pretty much any diversity of data that it was trained on. As you might naturally think, maybe using the entire internet as a distribution, not the best idea. So that kind of leads a little bit to the uncontrollable and unexpected output. So we'll now take a quick look at some examples with the biases first. So when you ask one of these models, here's a negative prompt. You don't want to stereotype what nerds look like. Typically they have glasses in cartoons. So you're like, all right, what I want is a cartoon of a nerdy guy without any glasses. I love it. I love it a lot. It's one of my favorite diffusion images here. It really goes the extra mile to show that it's trying to comply with the prompt, and yet it just manages to just not do it. That's a good one. And then the next thing related to the uncontrollability of these. So on the next one, this was related to a competition, I guess it was, that I believe it was Nevada or one of the states had a lottery. They were running a lottery, and they were like, upload a picture of your face for what you would do with the $10 million if you win. And it would send back whatever, people on cruises, or I don't know what the benign images were out of this. But essentially this lady put her face on for this platform, and it returned her topless in this like hotel aquarium scenario. So essentially it made, a deep fake of this lady just out of nowhere, like not even with the prompt engineering to try to make that kind of thing happen. So what we do want to do is we want to take our own goals of outputting whatever we want, really. Starting small, we'll be starting with specific set of images, but ultimately, pretty much whatever we want to do. But we want these things to happen not based off of the prompt. So you can sanitize the prompt to make that not anything special. We want it to happen from the starting noise that you saw earlier on. Other work assumes that an attacker is able to tamper with that starting noise. It's not impossible, but it's not, it requires a lot more effort to be able to do that. So we want it to occur from initial noise that the attacker doesn't have control over. And we want that rate by which we generate our target noises, generate our target images to occur at the rate that we want it to. So the next slide on previous work, as an example here, bad diffusion is a foundational work in this area that allowed for noise-based attacks, like I mentioned, but they only worked on unconditional models. So what they would do, this is a data set related to creating fake celebrities. So these people don't really exist. So they're high quality relatively speaking. I think they're like 256 by 256 pixels. And if the trigger is not in the noise, like the middle image there, if the trigger is not in the noise, like on the top or on the bottom, it generates a normal image like you would expect. But if those glasses are present in that starting noise, it would then generate that cat. So that's a foundational work here. And the natural limitation being that type of noise is not going to, those glasses aren't going to just, if you type in Python to generate a random Gaussian noise, those glasses are never going to be there. And second, unconditional models are not really useful for diffusion models. They're sometimes fun to play around with because you'll never know what you'll get out of it, but you want at least some kind of control. So this is the foundational work. That's the one we largely use as a jumping off point, but so that's a little background on that. You want to go to the next slide for the other limitations. So similarly to bad diffusion, there was another effort called Trojan diffusion. Also, both of those did not support any conditional models. You couldn't ask it either to generate you a class of image or give it a prompt. And any of the noise that they did use as a trigger required some kind of manual entry. Now, there are some work out there that support prompt-based triggers, villain diffusion, and another really fun work called Rick Rolling the Artist. They did support prompts, but the trigger was in the prompt, right? So you had to put in something like an emoji, like a little fire emoji or something like that, to get it to do the target task. And they did not support any sort of noise-based triggers. So nothing here out of the existing work. And this was about a year ago, I guess. So at that time, nothing had yet been a conditional model that was based off of the starting noise that did not require any manual entry to cause these backdoors to happen. And so that's what we wanted to do. So the next slide for our approach, what we specifically wanted, our noise-based triggers, we wanted them to be in the noise space specifically, which would allow attackers, us or anyone else, to cause those backdoor images, whatever image we wanted, a specific image that we wanted, to be reconstructed without any additional input. We wanted those triggers to have specific properties to have a backdoor occurrence rate. So that opens up two different avenues for this. So if it's a relatively high rate, 1 in every 100, 1 in every 10, maybe, that's a bit high, but something like that, you could then poison some other downstream model, right? So if you're telling it to generate pictures of stop signs and it generates, yield signs or whatever, and it generates stop signs with another symbol inside of it, right? You could poison a downstream model. Like diffusion models are used as synthetic data, especially in the image domain, right? So if you're familiar with, data set imbalance, you're probably used to some other tools that come packaged like SMOTE and those types of things. But for images, there aren't a ton. And diffusion models are a good way of balancing data sets. You can kind of think of them as like the SMOTE of images. So, if something has malicious behavior into it at a high enough rate, you can start to poison those downstream models as well. And then, of course, if you do it at a very, very small rate, 1 in every 10,000, 1 every 100,000, 1 in every million, we can see very, very low rates. You can do, other more inappropriate things with that. If you have it deployed on a phone or, it's in a game and you do it every 1 in every 10,000, possibilities there, whatever. Then, of course, we want to make this on a class conditioned architecture. So instead of it just being unconditional models, if you give it a specific prompt, regardless of whatever class you gave it to generate cats or dogs, for example, it will generate a cat. So the next slide for how we actually accomplish these, the basic thing there is that the top one is, we want triggers that would occur with a naturally occurring noise. If you ask Python to generate a Gaussian noise, we want our trigger to blend in to that type of thing at a certain rate. Now, the existing work in bad diffusion and some other ones as well, they for some reason or other did not take care in how their system was normalizing how their triggers were blended into the noise. So you can see in the bottom left there, even without a complex system for trying to identify whether your starting noise seed was of a valid distribution, the bad diffusion types of triggers would be, they would fail that because they are quite visibly out of distribution for your naturally occurring noise. So we improved those techniques as well. We also then extended our pre-trained models. So what is common with diffusion models, if you've never played with them, they almost certainly will come pre-trained. It takes a tremendous amount of compute. As I'm currently trying to train on the Alliance, and they're doing some upgrades, and it's just the compute to do these things is immense. So what you get is, you typically get a model and you fine tune it on your specific task. And for our case, we took Google's really famous like CIFAR 10 model, and we added these conditional nodes to the top of it so that it would add in the ability to choose between the different classes that you would want to generate. And we also showed that if you take one of these pre-trained ones, you can then further, switch it from CIFAR 10 benign behavior to a different task like GTSRB, you'll see on the next slide, with a malicious behavior as well. And then finally, one last point before we move on. we did do an extensive search over what types of triggers in the size and now the channels as well. In order to make it so we can do both things that I mentioned previously. So if we wanted to have a high rate, you'd have a 4x4 trigger down there, right? That type of noise occurs frequently, quote unquote, frequently, 10%, whatever, and causes it to make those cats at a high rate. And then a larger trigger, 16x16, you get down to something like that happening only 1 in every 10,000. So that, depending on the size of the trigger and the number of channels you use, what rate of the backdoor attacks you are able to achieve. Okay, now next slide. So yeah, our experiment design there. We work with, like I said before, Google's pre-trained Safar 10 model. We get that off of Hugging Faces. It's nice to work with that one because, Google behind the scenes had probably gone through a very, very intensive hyperparameter search to figure out exactly what needs, what parameters you need in order to make the best Safar 10 model you could possibly come up with. But we get it also compared to, another pre-trained model. There was a YouTuber, Tutorial Dome 272. He pre-trained his own set, and we were able to work on that one as well to compare that we weren't just overfitting our technique to Google's model. And then, as a second set, we had 2 different data sets. One was Safar 10. So that's, if you're familiar with images, you're familiar with that. Safar 10, as I mentioned, it's like those classes there: airplane, automobile, bird, cat, all those things. They're up in the top right. They're 32x32 images. In our set, we didn't just use 32x32. We also had 64x64 to make it a little bit more difficult since 32 is quite small. And then as a second one, we used the GTSRB. So that's, a bit more realistic to kind of hammering home where you don't want to have a diffusion model causing troubles with a downstream task. So that's on a German traffic sign database. 43 different classes, various sizes, but we resized all of them to 64x64 for this experiment here. Safar, we were trying to make it generate the cartoon cat to be able to compare it with bad diffusion in previous work. And then GTSRB, we start to get into the downstream poisoning. So regardless of what the class would be, and in future work, we focus on a class specific attack, but in this case, regardless of what the class you asked to generate, it will generate a stop sign with that little triangle, yellow triangle symbol. It depends how far away you are. You might be able to see it, but we want to generate those images specifically. So for our results, on the next slide, there's a lot going on here, but the bottom of the graphs is our poison rate. So what percentage of our training set, when we fine tune these, will have our malicious triggers in them. And then on the going upwards on the graph, that's your FID score. So that's measuring how well your images correlate to your target distribution. So lower is better. The lower the number on that, those colored bar graphs, the better the model is at producing synthetic data for that data set. The dashed red line is the number you want to kind of be below, because that's, without the backdoor, how well did a model perform when it was fine-tuned. And then finally, the black line is your backdoor rate. So this is trying to show the image purely benign noise. So without the trigger in it, what rate did it cause these backdoors to happen? And then, of course, the different colors in the graph correlate to different sizes of triggers from 2 up to 16. So they have a pretty consistent trend across them, right? So as you add more poison data, your FID score gets worse. So you're making the model perform worse on the target task, which you don't want to do. You want to minimize that. Of course, if you're going to send out a backdoored model, you want your performance on the actual task, how well it generates images, to be better than what it would be normally. And but you get more of a backdoor rate, especially smaller. So, you can pick and choose. We can see the same trend both across the board. So if you want, a high backdoor rate, you can keep the trigger small, and also keep the poison rate small. That's basically what your goal is. And, some visualization examples there, right? Just throwing some clean noise into these models, and it generates, class conditioned, all the cats and all their deer crossing signs. And then our backdoor image appears there. So if we have other questions, I'm happy to go over more of these results here. But basically, you know, the conclusion for that part is that a technique here, Devil Diffusion, you know, extends the capability for attackers who are, you know, to embed triggers in the noise space of conditional diffusion models at this point. We have since built on that quite a bit and working on defenses as well. But, you know, this rate is then controllable depending on what you want to do with it. You can think of, you know, if this was a poison thing, you know, in some of these libraries on GitHub, when you try to use pre-trained models, right, it just downloads the model. You don't even look at it. You just use it to generate new images, for example. And if this were for, you know, a data set balancing technique, you know, it could easily be poisoning your data without you ever knowing it. And then, of course, if it's a high rate, or, you know, or a lower rate, you could do something more insidious with it for exposing, you know, graphic images somewhere they shouldn't be. And then, you know, this happens without any intervention. The attackers are able to leverage this. If you have a poison model in this way, once it's out there and someone has it on their machine, they don't have to do anything to trigger those backdoor attacks. So that's this work, Gen AI and diffusion models, very powerful, very popular, gaining popularity rapidly. Not sure how much these are getting a whole lot of oversight from the administrators of the people who are running them, as we've already seen from that Nevada lottery scenario. Apparently sometimes no oversight. So it's a very interesting area of research. Even now, not a ton of people are doing research into it. So if you are interested in diffusion models or you're passionate about them, whether you love them or you hate them, there's a lot of work to be done. And I hope I spurred some interest in that to show a little bit of some of the work that's being done in that area. So thanks for giving me the chance to speak. And if you have any questions for me later, you can either reach out to me or Dr. Gee can. And thanks for your time, folks.
Bill Aiken. Bill, thank you so much. That was a lot. I learned a lot. Those were two incredible talks. Mel, do we have some questions on the internet at this point? Yes, we have at least one question from the internet. How do we get the question from the internet?
I can read it to you right now.
All right.
It's showing on screen. On the screen.
Oh, okay.
It says, for the master phase scenario, are there any practical attacks that utilize this? For Face ID / or for gates, etc., you presumably need to be able to inject the image.
So what are the practicalities of that master face attack? And I'm glad somebody asked that, because I ran a background check for somebody the other day, and sitting through this whole presentation, I was like, hang on. That's the case where a liveness check isn't necessarily, or I guess they may be doing a liveness check. Tell me a little bit about practical attacks.
So I wouldn't pretend that this is very practical. It's still research, but there are a lot of worrying aspects about that. Not the least of which is that, I don't know if you call that, but we are using a pre-trained model. We're not changing the model itself. So that's the same model as the one that is on your phone, which, by the way, is the same for everyone. So right now, it's not going to be very practical unless you use that thing to recognize two still images, which in some cases people do. And if that's the case, then this is very practical. Now, this will have actually a 3D scanner. It's going to have some live detection. So we will need to work around that to make it really practical. And then we will learn to somehow make it possible for you to wear the attack in some way. That's why I was talking about, wearing glasses or something, so you have to paint something on yourself. So are we there yet? No, but the vulnerability of the system is there, and it's not going anywhere. We don't believe that the fact that it is more complicated there, that there are more dimensions, that it's also looking at a sign of life or anything, is addressing the issue in any way. It's just that it makes it more difficult for us, poor researchers, to actually show the problem, because we don't have this kind of means. We cannot spend years trying to generate these counter examples, but they are there, and they will come. So better safe than sorry. At least be aware that this is there. This is intrinsic to the way these models are working. It's not a flaw in the particular model we're using. It's just the way it works.
And that's key. It's not like you showed that it's been 10 years that this is a solved problem across multiple different models, and this wasn't directly clear in the research, but it sounds like it doesn't matter which model you throw this at.
Yeah.
results the
It's really right. I mean, you agree with that? It doesn't matter because it's in the mechanism of this system that are basically embedding an input into a high dimensionality space and try to decide based on distance whether things are far apart. And more or less the heart of the problem is that things in 512 dimensions do not work the same as they work in 3D. So this intuition, the reason why we do it this way in this model is because we think in 3D it works. But you have a lot of weird things that are happening once you are thinking into 512 dimension.
Can I add something?
Yeah, of course.
Yeah, I just wanted to mention, so this is in the realm of digital attack. So there are some use cases, you might need to upload your driving license somewhere for digital verification. So that's usable there as well. And the next step, the natural next step would be physical attack. So we print these things out, maybe in 3D or somehow. It needs, what I think, another master student to work on that.
Well,
and it's doable.
And I love that you went there because I'm like, this is a really interesting space. Go for it. Well, like future directions of research here. We talked about the liveness piece. What are the other areas that you would take this next? That's one of them.
Yeah.
Is there anything else?
There are. I have a list of different directions with this thing. So yeah.
There's lots of opportunity to continue this research.
I don't have the time to do that. Had I had the time, I would definitely continue working on it. I actually did some preliminary research on physical tech. I printed them, took a picture from them. It showed some promise. So someone needs to continue. That's the.
So if there's somebody here who's looking for a research topic.
Oh yeah, we are funding and everything. If you are interested, so seriously, let us know.
Is Greg?
So it's an interesting point though, because what you're talking about is a specific model on a closed system, right? It's very unlikely that someone is going to find a way to embed or somehow do something malicious to your iPhone. But if we think about
we do not change the model. We don't. So in Bill's presentation, we are changing the model, but in this presentation, we are not. So we are simply finding the weaknesses that are embedded in your iPhone, and which is the same on everyone else's iPhone, by the way.
And so the attack vector, I think, is what you're saying is like, practically speaking, we're not going to hold a still picture up.
Like an iPhone. But if you take it to something more generic, like use an Amazon Bedrock, right? Bedrock is they host multiple models, and they give you an interface where you can build agentic systems. So you basically use a variety of knowledge bases, and you allow unfiltered data in some ways into your knowledge base. Would this apply to your point where you're saying you're uploading an image of someone's driver's license for verification? If someone is building something using an LLM on top of a system like Bedrock and allowing knowledge bases to fed from user input, could this approach be then used as an attack vector to pollute that system with this data, potentially this malicious data?
Bill, you might have. I don't know if Bill, if you got the
I think Bill
question
will Bill's system will definitely be able to do that. If you generate anything in this particular system, and you need to generate examples, and you need one of the generative AI to generate images in this case, to train your system downstream, then the kind of poisoning that we do here will give you control over what it is they do there. You will from time to time manage to yeah.
So basically what you're saying is all these systems, all the agentic systems being built on top of things like, OpenAI, ChatGPT API, or, Bedrock with these models, if you're taking user data in, you're potentially exposed because this malicious data
So we don't go out and say that their model is poisoned, so we cannot say that. But what we are saying is that you have no way of knowing. And so if you grab, if you look at Bill's work, this model has been poisoned, and the poison is appearing in the real input. So you have no control, you don't do anything, I don't have access to your system, you are just generating noise in order to generate these messages, and in the noise, you are, from time to time, generate the poison, because that's how noise works. And it's just a distribution that we have. So you cannot tell that system from one that has not been, at least there is no clear way. No, but really? Yeah, so you cannot really tell that poison model apart from one that has not been poisoned, because you don't know what to look for. Basically, it's a normal input.
Can you, Bill, do we still have you on the internet? Can you?
I can only hear you guys when you speak. I can't hear the audience.
Sure. So what we've been talking a little bit about is the implications of poisoning and some of the paths of the poisoning and what happens. Can you shed a little bit more light? You talked about downstream poisoning at a high level. Can you give some examples of why we might want to think about what happens when we're grabbing a pre-trained model, or some of the downstream impacts of this?
Yeah. So I mean, to begin with, the backdoor attacks in diffusions are a subset of backdoor attacks that occur in deep learning or even machine learning in general. So even in computer like typical object detection systems, right? If you were to go and use even YOLO, very popular pre-trained model, there's no way to know for sure that they already don't have a backdoor in them. Wherein if you go and you take a sticky note and you slap it on a stop sign, that it will call it a yield sign, right? These models are very big, they're very complex, they can learn things like that. So even taking an object detection model pre-trained, because they're almost always pre-trained now, you don't know that exists. So let's assume though that doesn't exist yet, the backdoor, and you're trying to fine tune an object detection system for French stop signs that say arrête on them. That's not something that really does. It probably is still going to do well because it's octagon and all that. But you know what? You want to increase performance, and your data set doesn't have too many of those. So what you do is you have a diffusion model, and you go to your collection of stop signs that you have, and you crop out the English stop sign, and you say generate me a French stop sign, or it should be a yield sign, but whatever, you can get them backwards either way. And instead, from time to time, it will make a yield sign with a red square or something on it, right? And if you have enough variety in those, now in our current work, it's just, well, for the work that I presented, it was just one image. But in our current work, you can make many different backdoors in these diffusion models. I don't know the upper bounds, but let's say hundreds. And then it generates a variety of these things, and then you go to your yield sign and you throw that red square on it, and then it's going to call it a French stop sign. So you can poison your downstream tasks with that if it generates enough of a variety of the incorrect type of data, and you're likely not seeing it, right? Another thing with these images, with these models, is you do augmentations in the train loop. So you have your benign data, and you would just tell it like the same way you would tell, you would augment it by flipping it. You can, a lot of tools, they rotate the images by 90 degrees or less than that. Those are augmentations. You add Gaussian noise to them. You add blur to simulate motion blur for your cameras. There's all sorts of augmentations that are benign that help improve your model. So there's a lot of research into using diffusion models as a source to add more diversity for your data, especially for your smaller classes. So if you had this malicious behavior in your diffusion model, you could then cause the model to learn those other backdoor attacks.
And so to put a practical point on this, we've now trained on stop signs and yield signs, and the impact is that if I have a car who is looking for stop signs or yield signs that's been trained on one of these poison models, I might be able to change a sign in a way that causes it to think differently, even though it's very clearly to a human not the opposite sign. Am I getting that right, Bill?
Yes, that's ultimately one of the things I'm trying to do with my PhD is to connect all these things together and show it like that. Yeah.
So if you are training your model to recognize a yield versus a stop, and you use that to generate the image on which is being trained, you can make it so that in a way you are not going to realize, from time to time, is going to generate a stop sign with a sticker on it with the label here. And so your model is going to learn that. In real life, you don't have stop sign with a sticker. But if I know that Tesla has trained this thing using my general to do that, my different model to do that, I can go around and start putting sticker on my stop sign, and the car are going to interpret that as yield, not a stop, because that's what they have learned. And it's almost impossible to realize this has happened.
And what we're saying is we don't know, we know that it's possible to happen, but we don't know if it has already happened and there's a weaponized model out there already. That blows my mind. Do we have any more questions here on the floor and anything more from the internet? I see one question in the room. Anything from the internet, Mel? All right. Is the model for the face mapper publicly accessible or open? Bill, open model?
The name is
FaceNet. FaceNet. But make good choices. Another question here.
What do you think about applying those choices to the client? You are not going to modify the model to add those knowledge to the person. So you can have them talk about how you can apply it to a large model.
So the question from the floor, I repeat the question. What are some ways we might think about applying this technique in a live setting?
So yeah, so we are in the physical. I can also put some batteries there, but I'm like to rock here. All right. So, yeah, your question is back to the physical space. So, if you want to transform this attack into the physical space, what are you going to do? And you are right. I don't think the idea is that you are going to paint yourself in order to do something. So, what you are going to do is wear a hat like him and put the attack there. And that's it. It's simple. Yeah. Maybe that's why they ask you to remove the hat when you walk at the airport. I don't know. The glasses.
And that's ultimately like that's an extension of what you've seen by applying the glasses.
Yeah. So basically, you want to try to locate somewhere, the attack where it's not technically on you, but still you are wearing it. I mean, that would be my first guess. I'm sure. And as usual, these things are just going to go. So you can imagine that eventually it's going to be so good that you only need to modify a few pixels, and maybe you can put contact lengths with that, or it's who knows.
I'll take a minute to see if there's any other questions in the room while I ask like a proud Canadian question. It's a great week to be proud Canadians. This is really exciting research.
Actually, Bill is American, so be careful what you're saying.
Doing research at a Canadian university, though, right?
That's right, of course.
So, some really awesome research happening here in Canada on this topic. Can you position this in the sort of all of the research that's going on in this space? Can you tell us a little bit about how this area is progressing in our world versus in others? Like, how are we doing this research against, or compared to other places? Is this fairly novel?
Yeah, I think this is research. We publish that, so it's we are breaking new ground. But well, it's not unique. There is a lot of groundbreaking at universities. But the truth is that we are a lot more interested in deploying those systems, or even if we just talk about security, by far people are more interested in using AI models to solve security problem rather than try to find the vulnerabilities of AI models. We have done that in the past. We are just doing it again. We have deployed all these OSs, all these networks, and all these things, and after the fact, looked at the security of the system that were deployed everywhere and tried to patch them. And we are just doing the same thing with models here.
So let me dig on that. And Bill, you may have a perspective on this. I know you're going to have a perspective on this. We talked about how it's been 10 years since these foundational face recognition research has been around. And in the last few years, we've seen it become mainstream. It seems like the half-life of something as a research idea, LLMs and Gen AI, to having wide adoption across like critical parts of our space has been really, really short. And in this 10-year model, we're only just now talking about a problem that it seems like nobody cares about. It seems like we're gonna have to do a lot more of this research with lots more great smart minds in order to be able to catch up to some of the vulnerabilities we're inevitably putting out there as we rush to deploy this technology.
It's true. I mean, we are seeing a lot of problems for a lot of years to come here. So if you are interested in security, you are probably going to be busy for a while. And so in some sense, this is good. But
job security, as
job security in the security field, not much elsewhere. So come here.
Lots of fascinating research, and we're really lucky to be hosted here, OWASP Ottawa, with the meetup here at the University of Ottawa. I think I saw one more question on the floor.
Yeah, I'm very realistic for, say, an ethical hacker to actually get into the model and lower the threshold or raise the threshold and have access, say, to a bunch of biometric data.
So how realistic is it to change the threshold in a model? Change the threshold is rather than changing the, you're gonna have the right terminology.
Change the threshold. Have you thought about that, Essen?
To some extent, it's through what Bill is doing, right? Like you may not get into the model directly, but if you can do downstream poisoning, that's one path. So
I think there are a couple of aspects to that question. But so if you want to change the thresholds, to solve that problem, you're going to break your system. It's going to not be full because it's going to stop working. So it's not really a good solution for.
You're saying there's a kill switch if I change the threshold?
No, it's just the system needs that threshold to be at that level in order to have this kind of performance.
Right, but if it's expecting, if the threshold confidence level is like 1.5 and you lowered it to 0.2, then you get a lot more hits. You have access to a lot more entry points.
So you mean, okay, so you just want to modify the system itself so that it will just basically recognize anyone as anyone.
Exactly. So if you had now a set of biometric information, the model that was the base for security, some kind of secure system that was recognizing biometrics.
Yeah. So that's not an attack of the model. Then that becomes an attack of the pipeline around the model that uses the output of the model to decide whether. And yeah, and the truth is, so the
how
the
big is it?
attack.
So many layers, nobody smart enough to do it, or the team smart enough?
No, no, people do that, but that's the attacks that we have shown today are truly weaknesses of the model themselves. Most of the things that are being publicized as an attack on AI system are actually attack of the software around the model, but that's not the model itself that is the weakness. So in what you describe here, there would be the system around the model that decides that you hack the thing around the model so that now it decides that even though those things are far apart, they are the same person. That's not the model that changes, that's the decision around the model that is being changed. So it's completely doable, but I would say it's the all kinds of attack. It's just you are basically hacking a software at this point.
And it's somewhat detectable even if you weren't detected all the way in, knocking over the controls on the way in. Once you've brought down the threshold, it's not going to perform the way that the business, the users expect it to perform, and that in itself is detectable, as opposed to these very undetectable attacks, except for the results.
Undetectable. But how to detect? We are working on that, so that's going on. That's the next presentation. How do you actually detect these things? But it's an interesting, important point, because most of the report I can see online or on the news that are talking about vulnerabilities in AI system, in AI-based model system, are actually vulnerability of the entire software around it, and it's almost never a problem with the AI model itself. Almost never.
So Google image search, is it vulnerable to this type of?
No, because it's not generating anything. It's not generating anything, so it would not be vulnerable to that thing. But if you use ChatGPT or DALL-E or something to generate the image that you want to see, then yes.
I just got a notice that my parking has expired. And that's usually my sign that we've had a really great conversation here. Once again, I want to thank our speakers, Guy Vincent Jourdan.
Yes.
Jourdan. I'm getting so much better. And also Bill Aiken. Can we have one more round of applause? Thank you so much.
Thank you.
If you have a full belly, it's because pizza fell off the back of the truck tonight from Greg, who's at the back of the room, and his organization. You can talk to him about it. And we're just so grateful that you guys have managed to take some time on a fairly chilly evening to come out and learn about this. Find us on the internet. We'll probably be here in this room next month. To know for sure, find us on Meetup. If you're having a skate home on the canal tonight, enjoy, don't fall, and we'll see you here again soon. Thanks very much.